May 2, 1945. 11:20 hours. Oberjoch, Bavaria. Wernher von Braun sat in the back of a commandeered Opel truck, his left arm in a makeshift sling from injuries sustained in a car accident 3 weeks earlier. The convoy of German scientists and engineers had been driving south for 4 days, fleeing the advancing Soviet armies that were sweeping across eastern Germany with the momentum of 6 million men bent on revenge. Around him, 12 of his senior staff from Peenemünde carried whatever technical documents they'd managed to save from the systematic destruction ordered by SS officers who'd preferred burning rocket research to allowing it to fall into enemy hands. The truck stopped at an American roadblock near the Austrian border. Von Braun watched through the canvas cover as GIs approached with rifles ready, expecting resistance or at least bureaucratic complications that would delay them long enough for Soviet forces to catch up. Instead, von Braun stood awkwardly with his injured arm, walked toward the nearest American soldier, and spoke in carefully practiced English. "My name is Wernher von Braun. I am the technical director of Peenemünde Army Research Center. We wish to surrender to American forces." The soldier stared at him, clearly uncertain what to do with a German who spoke English and claimed importance beyond typical Wehrmacht personnel flooding south to escape Soviet capture. Von Braun continued speaking, his accent heavy, but his words precise from months of preparation for exactly this moment. "We have information that will be valuable to the United States. We developed the V-2 rocket. We can build more advanced systems. We choose to work for America rather than the Soviet Union." The statement represented calculation that von Braun had been making since late 1944, when German defeat became inevitable rather than just probable. He'd spent 12 years developing rocket technology for Germany, first under the Weimar Republic as a young engineer fascinated by space travel, then under the Nazi regime that had funded his research because rockets could deliver explosives across hundreds of miles. Now, Germany was collapsing, and his choice was simple: surrender to Soviets who would extract his knowledge through methods he preferred not to imagine, or surrender to Americans who might value his expertise enough to treat him as asset rather than prisoner. The American soldier called for his commanding officer. Within 2 hours, von Braun and his team were being transported to 7th Army Intelligence Headquarters, where officers who actually understood the significance of Peenemünde rocket research began asking questions that would continue for weeks. The weapon that reached space. The V-2 rocket that had made von Braun valuable to American forces represented technological achievement that exceeded anything developed by other nations during the war. The missile stood 46 feet tall, weighed 28,000 pounds fully fueled, and could deliver a 1-ton warhead across a range of 200 miles while reaching altitudes of 55 miles, technically touching the edge of space before descending toward its target. The engineering required to create a functional liquid-fueled rocket that could operate reliably under combat conditions had challenged German scientists for more than a decade. Von Braun had begun working on liquid fuel rockets in 1932 as a 20-year-old graduate student, joining a small group of engineers who believed that rockets could eventually reach beyond Earth's atmosphere. The German army had funded this research beginning in 1932, recognizing that rockets represented potential weapon system that Treaty of Versailles restrictions didn't explicitly prohibit. By 1937, the Army had established the research facility at Peenemünde on the Baltic coast, providing von Braun with resources that exceeded anything available to rocket researchers in other countries. The facility employed 4,000 workers at its peak, operated wind tunnels and test stands that could handle full-scale rocket firings, and consumed budgets that rivaled German expenditure on atomic weapons research that never produced functional weapons. The V-2 had entered operational service in September 1944, too late to affect Germany's strategic position. but early enough to launch approximately 3,000 missiles against Allied targets before the war ended. London received more than 1,500 impacts. Antwerp and other Belgian cities absorbed most of the remainder. Each missile carried a warhead containing 1,650 pounds of amatol explosive that created blast effects comparable to small bombs delivered by conventional aircraft. The weapon's military effectiveness had been limited by accuracy problems that made precision targeting impossible and production costs that exceeded the damage each missile inflicted. Building one V-2 required approximately 12,000 man-hours of skilled labor, consumed rare materials including alcohol fuel and liquid oxygen, and cost roughly 100,000 Reichsmarks, equivalent to the price of 2 fighter aircraft that could deliver greater explosive tonnage with higher accuracy and reusability. But V-2's military limitations obscured its technological achievement. This was humanity's first vehicle to reach the edge of space, the first operational ballistic missile, and the first weapon system that demonstrated feasibility of rocket propulsion for purposes that extended beyond atmosphere. Von Braun understood this distinction clearly. Every V-2 launch was simultaneously a weapon strike and a proof of concept for technology that could eventually enable spaceflight. His famous comment about the V-2, "The rocket worked perfectly, except for landing on the wrong planet," captured the duality that had defined his entire career. He'd joined Nazi Germany's military research establishment because it provided resources for rocket development that wouldn't have existed otherwise. He'd designed weapons that killed approximately 9,000 civilians because that was the price of advancing technology he believed would ultimately serve peaceful purposes. The moral calculation was complex, troubling, and entirely characteristic of how totalitarian regimes exploited scientific talent for purposes that researchers justified through belief that knowledge itself transcended political circumstances. American intelligence officers who interrogated von Braun during May 1945 recognized immediately that they'd captured not just technical information, but the human embodiment of Germany's most advanced aerospace research. The challenge was determining how to exploit that knowledge without creating political complications that would undermine public support for employing enemy scientists whose work had killed Allied civilians. Operation Paperclip and the Moral Calculus. The decision to bring German scientists to America had been developing for months before von Braun's surrender. American and British intelligence had been tracking German research programs throughout the war, compiling lists of scientists whose knowledge would be valuable during post-war competition with the Soviet Union, that everyone understood would replace wartime alliance with ideological confrontation. Operation Overcast, the initial program for exploiting German scientific expertise, had been authorized in July 1944 by the Joint Chiefs of Staff. The program allowed temporary visits to the United States by German scientists who could contribute to ongoing war effort against Japan. By early 1945, as Allied forces advanced into Germany and the extent of German technological achievements became clear, American planners expanded the program into what would become Operation Paperclip, a systematic effort to identify, secure, and recruit German scientists before Soviet forces could capture them. The name Paperclip derived from the administrative practice of attaching paperclips to folders of scientists approved for recruitment, distinguishing them from the larger population of German technical personnel being processed through standard prisoner-of-war procedures. The operation eventually brought more than 1,600 German scientists, engineers, and technicians to the United States between 1945 and 1959, with von Braun and his rocket team representing the most valuable and politically complicated group. The American government made the calculation that acquiring German rocket expertise justified overlooking or minimizing Nazi affiliations that would normally have resulted in war crimes prosecution. Von Braun and his team were processed through military intelligence channels that sanitized their backgrounds, removing or obscuring evidence of party membership and reducing their histories to technical achievements rather than political activities. The sanitization was deliberate policy based on assessment that Soviet acquisition of German rocket scientists would create strategic disadvantage that outweighed moral considerations about employing former enemy personnel. The first group of rocket scientists, including von Braun, arrived at Fort Bliss, Texas, in September 1945 under military custody that was officially described as protective rather than punitive. They were housed in military barracks, required to wear identification badges at all times, restricted from leaving the base without authorization, and forbidden from discussing their work with anyone outside approved channels. The conditions resembled detention more than employment. But the Germans understood clearly that their situation could have been far worse. The desert years. Fort Bliss and the adjacent White Sands Proving Ground in New Mexico became the center of American rocket research for 5 years after the war. The facilities offered vast empty spaces suitable for test launches, isolation that minimized security risks, and distance from population centers that might object to having former Nazi scientists working nearby. Von Braun's team began by teaching American engineers and military officers everything they knew about V-2 technology. The Germans had brought technical documentation, but understanding paper designs required practical demonstration that only the original developers could provide. The Army had shipped approximately 100 captured V-2 rockets from Germany to White Sands, along with enough components to assemble more from spare parts. Between 1946 and 1952, the combined German-American team launched 67 V-2 rockets from White Sands, each flight providing data that advanced American understanding of ballistic missile technology. The launches revealed how far American rocket development had lagged behind German research during the war. The United States had focused on conventional weapons and nuclear bombs delivered by aircraft, treating rockets as experimental technology that wouldn't affect the conflict. The V-2 flights at White Sands demonstrated operational reality of ballistic missiles that could strike targets hundreds of miles away with minimal warning, a capability that suddenly seemed critically important now that wartime alliance with the Soviet Union had transformed into Cold War competition. Major James Hamill commanded the military unit that supervised German scientists at Fort Bliss. His initial responsibility was ensuring security rather than facilitating research, making sure von Braun's team didn't escape, didn't communicate with unauthorized contacts, and didn't create embarrassing incidents that would undermine Operation Paperclip politically. But Hamill quickly recognized that treating the Germans purely as prisoners rather than collaborators reduced their effectiveness and morale. He established procedures that gave German scientists increasing freedom as they demonstrated reliability and integration into American programs. By 1947, they could leave the base for approved recreational activities. By 1948, they could apply to bring families from Germany. By 1949, the restrictions had eased enough that their status resembled foreign contractors rather than detained personnel, though their immigration status remained deliberately ambiguous. Von Braun adapted to his new circumstances with the same pragmatic flexibility that had characterized his entire career. He learned American idioms, studied American culture, and presented himself as an enthusiastic convert to democratic values who'd been trapped by circumstances in serving Nazi Germany, but now embraced opportunity to contribute to American defense. Whether this representation was genuine transformation or calculated performance remained matter of interpretation that depended on whether one believed people could fundamentally change their beliefs or merely their expressed allegiances. The technical work during the Fort Bliss years focused on incremental improvements to V-2 technology rather than revolutionary advances. The Germans taught Americans how to handle liquid oxygen, how to test rocket engines, how to integrate guidance systems, and how to troubleshoot the thousands of problems that arose when trying to launch complex vehicles that operated at the edge of contemporary engineering capabilities. The knowledge transfer was systematic and thorough, transforming American military personnel from novices who barely understood rocket principles into competent engineers who could eventually develop their own designs. Von Braun used this period to cultivate relationships with American military officers and civilian officials who would prove valuable as rocket research transitioned from military experiment to strategic priority. He wrote articles for military journals, gave presentations at technical conferences, and positioned himself as spokesman for German expertise, rather than just another foreign scientist working under contract. The strategy proved effective. By 1950, von Braun had become the public face of Army rocket research, the German expert who could explain complex technology to audiences without technical backgrounds. The Redstone and the Army's ambition. In 1950, von Braun and his team transferred from Fort Bliss to Redstone Arsenal in Huntsville, Alabama, where the Army established its primary rocket development facility. The move represented both geographic relocation and substantive shift in status. The Germans were no longer detained personnel under military supervision, but civilian employees of the Army working under standard government contracts. Huntsville transformed into America's rocket city over the following decade. The population grew from 16,000 in 1950 to 72,000 by 1960 as military personnel, civilian contractors, and support industries followed the Army's rocket program. Von Braun became the city's most prominent resident, his German accent and distinctive appearance making him instantly recognizable at restaurants, churches, and public events, where he represented both the exotic scientist from Germany and the local employer whose work supported thousands of jobs. The technical focus at Huntsville was developing operational ballistic missiles for the Army. The Redstone missile, which von Braun's team began designing in 1950, represented evolutionary improvement on V-2 technology rather than revolutionary advance. The missile used the same basic liquid fuel engine design, but incorporated improvements in materials, guidance systems, and reliability that reflected American engineering standards and manufacturing capabilities. Redstone stood 69 feet tall, substantially longer than the V-2, and could deliver a nuclear warhead across a range of 200 miles with accuracy sufficient for strategic targeting. The first successful test launch occurred in August 1953, validating the design and establishing the Army's credibility in ballistic missile development that had become a critical component of nuclear deterrence strategy. But von Braun's ambitions extended beyond military missiles. He'd spent 20 years dreaming about space travel, had written extensively about lunar missions and Mars expeditions, and believed that ballistic missile technology developed for weapons could be adapted for peaceful exploration that would capture public imagination and justify continued investment in rocket research. In 1952, von Braun published a series of articles in Collier's magazine describing detailed plans for space stations, lunar expeditions, and Mars missions based on existing rocket technology scaled up to sizes that would enable human spaceflight. The articles featured elaborate illustrations showing rotating space stations, three-stage moon rockets, and fleets of spacecraft crossing interplanetary distances. The vision seemed like science fiction to readers in 1952, but von Braun presented it as an engineering problem that could be solved through systematic application of principles already demonstrated in military missile programs. The Collier's articles made von Braun famous beyond military and technical circles. He appeared on television programs, gave public lectures, and became America's most prominent advocate for space exploration during the 1950s. His status as former German scientist gradually transformed into something approaching celebrity as public memory of V-2 attacks faded. and Cold War competition with the Soviet Union made space achievement seem like measure of technological and ideological superiority. Sputnik and the space race, October 4, 1957, changed everything. The Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth, using ballistic missile technology adapted from their own captured German scientists and indigenous research that had advanced faster than American intelligence analysts had believed possible. The psychological impact in the United States was immediate and profound. If Soviets could launch satellites, they could launch nuclear warheads that would strike American cities with minimal warning. Von Braun had been arguing for years that the Army should be authorized to launch American satellites using modified Redstone missiles. The Defense Department had rejected these proposals, assigning satellite development to the Navy's Vanguard program that used rockets designed specifically for civilian scientific purposes rather than military weapons. The decision reflected political calculation that America's first satellite should appear peaceful rather than militarily threatening, avoiding impression that space exploration was simply extension of arms race. Vanguard failed spectacularly. The first launch attempt on December 6, 1957, ended with the rocket exploding 2 seconds after ignition in a televised disaster that newspapers labeled Flopnik and Kaputnik. The failure created public humiliation that demanded immediate response, and the response was turning to von Braun's team at Huntsville. The Army authorized von Braun to prepare a satellite launch using the Jupiter C rocket, a modified Redstone that had been test-firing at extended ranges for 2 years. Von Braun's team worked around the clock for 3 months, adapting military hardware for satellite launch and integrating Explorer 1, a scientific payload built by Jet Propulsion Laboratory that weighed 31 pounds and carried instruments to measure cosmic radiation and temperature in space. Explorer 1 launched successfully on January 31, 1958, from Cape Canaveral, Florida. Von Braun stood in the blockhouse during the launch, watching instruments confirm that his rocket had delivered America's first satellite to orbit 64 days after Vanguard's failure. The success made him a national hero overnight, the German scientist who'd redeemed American pride by matching Soviet achievement and proving that the United States could compete in space, despite Sputnik's head start. The public narrative of redemption was powerful and convenient. Von Braun had come to America as enemy prisoner, had worked for more than a decade on military missiles, and had now delivered space success that transformed him from former Nazi into American patriot. The transformation required forgetting or minimizing his V2 work, his party membership, and his connection to slave labor at Mittelbau Dora. Most Americans were willing to forget because the Cold War demanded heroes who demonstrated American technological superiority, and von Braun's narrative of transformation served that purpose perfectly. NASA and the Saturn program. The creation of NASA in July 1958 represented the federal government's response to Sputnik and recognition that space exploration required civilian agency rather than military program. The Army's rocket team at Huntsville transferred to NASA control in 1960, becoming the Marshall Space Flight Center with von Braun as director. The transfer meant von Braun's work would focus exclusively on space exploration rather than military weapons, a transition that aligned perfectly with the public narrative of peaceful scientist whose weapons background was unfortunate necessity rather than defining characteristic. President Kennedy's announcement in May 1961 that America would land humans on the moon before the end of the decade created the mission that would define von Braun's remaining career. The lunar landing program required rocket far more powerful than anything yet built, a vehicle that could launch spacecraft weighing more than 300,000 pounds toward the moon, requiring engines that generated millions of pounds of thrust. Von Braun and his team at Marshall began designing the Saturn V rocket in 1961. The vehicle represented engineering challenge that exceeded V-2 development by orders of magnitude. Saturn V stood 363 feet tall, weighed more than 6 million pounds fully fueled, and generated 7.5 million pounds of thrust from 5 F1 engines that each burned 3 tons of kerosene and liquid oxygen per second. The scale was unprecedented. Saturn V remains the most powerful rocket successfully operated in human history. Developing Saturn V required solving thousands of technical problems that hadn't existed with smaller rockets. The F1 engines experienced combustion instability that caused destructive vibrations until engineers developed injection system modifications that stabilized burning. The fuel tanks had to be built from aluminum alloys that could withstand cryogenic temperatures without becoming brittle. The guidance system had to navigate accurately across distances of 240,000 miles. The integration of stages, engines, and spacecraft had to function perfectly because no test flight could fully simulate lunar mission conditions. Von Braun applied management techniques he'd learned during 20 years of rocket development, creating systematic testing programs that identified problems before they caused failures. Every component was tested individually, then in combinations, then as complete systems. Test stands at Marshall subjected engines to conditions exceeding flight requirements. Manufacturing quality control maintained standards that rejected components with flaws that might not cause immediate failure but could lead to problems during actual missions. The program's cost was staggering. Saturn V development consumed approximately $6.5 billion between 1961 and 1973, equivalent to roughly $50 billion in current terms. The expenditure represented national commitment to space achievement that reflected Cold War competition more than scientific necessity, but the technical results validated the investment. Saturn V flew 13 times between 1967 and 1973, with every launch successfully placing payloads into intended orbits, and all but one mission accomplishing its objectives without major problems. The architect of tomorrow, von Braun, remained at NASA until 1972, directing Marshall Space Flight Center through the final Apollo missions and early planning for the Space Shuttle program that would eventually replace expendable rockets with reusable vehicles. He retired from NASA in 1972 to become vice president of Fairchild Industries, a private aerospace contractor, but continued advocating for space exploration through public lectures and writings that maintained the vision he'd articulated since the 1920s: human expansion into space as inevitable next step in civilizational development. He died on June 16, 1977, at age 65, from complications of cancer. His obituaries described him primarily as the architect of America's space program, the visionary who'd led development of rockets that carried humans to the moon. The Nazi past received mention, but was generally treated as unfortunate early career phase that he'd transcended through subsequent achievements. The moral reckoning with von Braun's legacy remained incomplete at his death and continued for decades after. He'd designed weapons that killed thousands of Allied civilians. He'd worked within Nazi Germany's military-industrial complex that used slave labor from concentration camps. He'd prioritized technical achievement over humanitarian concerns in ways that suggested moral flexibility at best and complicity in war crimes at worst. But he'd also helped establish American preeminence in space exploration. He'd mentored generations of engineers who would continue advancing rocket technology. He'd captured public imagination with visions of spaceflight that inspired millions to support scientific endeavors. The contributions were real and significant, transforming humanity's relationship with space in ways that extended beyond Cold War competition or national prestige. The paradox of von Braun's career, that the same person could design weapons of mass destruction and rockets that enabled peaceful exploration, reflected broader tensions in how technological development served both destructive and constructive purposes, depending on political context and human choices. The V-2 and Saturn V were fundamentally similar machines serving opposite purposes, demonstrating that technology itself was morally neutral, while applications could be profoundly good or evil. American willingness to employ von Braun, despite his Nazi past, represented pragmatic calculation that acquiring expertise justified overlooking moral complications. The calculation proved correct in narrow strategic terms. American space achievement benefited enormously from German knowledge that might otherwise have been lost or exploited by Soviet competitors. But the calculation also normalized practice of prioritizing technical capability over moral accountability, establishing precedent that would complicate future debates about whether expertise justified clemency for those who'd served criminal regimes.